What's up, guys? Welcome to Lab Report 3 for Physics 2211. I'm Sammy. Let's get right into the video. Introduction. This lab was about using energy balances to find orbital systems data. To do this, we need a few equations. Centripetal force is equal to mv squared over r. The change in energy is equal to the change in kinetic energy plus the change in potential energy. And the change in energy, which is also what I just said, is equal to Q plus W. So change in heat, basically, and work. And then also force of gravity is equal to the gravitational constant G, and then the two m's multiplied together over r squared. And the point of this lab is to prove that every variable in a circular motion problem is related to one another. So if you have the minimum amount of variables required, you can find every other variable through these equations. Alright, for the black hole, first we just find momentum, which is velocity times mass, and then to find the change in that, just final minus initial. And now that we have the change in momentum, the change in momentum over the change in time is equal to force net. We show that right here. Because force is mass times acceleration, and momentum is mass times velocity. So if you have mass times velocity over time, you have mass times acceleration, which is force. And then we just basically find the unit vector here, which is just the momentum vector over the magnitude of the momentum vector, and do all of that stuff. So we just put that over time and multiply the change in the magnitude of the force net times the unit vector of momentum to find the parallel force. And then the aspect of the force that is not parallel has to be perpendicular, just by definition. Then we take the average of all of the masses of the black holes at each instant to find our answer. The mass of the black hole is 4.925 times 10 to the 20th. And that's just the little animation there. Now for the spaceship, basically you just have to find the position vectors all relative to each other and do the force of gravity calculations to find the force of gravity combined, which is the net force, on both the spaceship and the moon. The planet doesn't matter here because it's so big it's negligible. And we just do those calculations to set up. Oh, of course we have to use the momentum principle to do motion at the bottom there. But we just do that to set up this, and our initial velocity was given by our instructor, and it looks like this in my calculation. Possible errors. Taking the average of the black hole's mass. Coding errors, probably made a bunch of those, but hopefully not too many. And because there is no data from real life, I mean, we're just working with theoretical values, so there shouldn't be like margins of error other than just genuine mistakes. Questions. What's the relation between change in momentum over time and force? Change in momentum over time is equal to force, because momentum is mass times velocity, velocity over time is acceleration, so mass times velocity over time is equal to mass times acceleration, which is equal to force. How would the entire system of the black hole and the little planet move, with the star of course, is that all of the gravitational pulls would affect each other and they would all orbit around each other. But because like the star and the black hole are so big, the black hole wouldn't really look like it was moving, and the star would move in proportion to the black hole, but it wouldn't be apparently moving in proportion to the small planet. So it would just look like how our sun looks, with like Earth and Mercury and all the other planets circling it. Thank you!